So it's time to say hello. Well, it's a great pleasure to see, I can actually see some of you here this evening. It's not been an entirely successful year as regards presentations and knowing what's going to happen next. And of course, this one has been another one of those surprises. But I'm so grateful to all of you who've come along throughout the year. And now we're into the last of the series of these voyages in space and time, but now, I suppose, in greater space than normal. And it's an enormous pleasure to welcome Monica, who's a friend of the school and who has also already spoken in these Tuesday evening series. She was undergraduate at Durham University, where she read geology and chemistry, and then went to Cambridge for a PhD, where her supervisor was that terrific character, Colin Pillinger. And then she went to the Open University, to the Natural History Museum, where I happen to know her for over many years, and is now back at the Open University as a professor. I think she's a splendid ambassador for her science, both for her enthusiasm and also the way that she communicates things which for me are really quite difficult to comprehend, such as space and time. A fantastic communicator, and I greatly envy her depth of knowledge. So, Monica, over to you. At the end, maybe you'll take some questions.
Of course, yes. Okay, thanks very much, Diane, for the invitation to come and speak here. And I'm really, really sorry that I couldn't be there in person. I had hoped to be, but family circumstances meant I can't. And I've also changed the title of my talk, all right? It was Voyages in Space and Time, but I think actually it'd be much more appropriate to talk about voyages in space and time, with the voyages in question being meteorites. And I want to share with you some of the information that we can get from meteorites and why I consider them to be voyages in space and time. So, right, okay, so fallen at the first hurdle. Can't advance the slide. Why can't I advance the slide? No, why can't I advance the slide? Carriage return, there we go. All right, now try again. Right, so this is a simulation of what the solar system might have looked like about 4,567 million years ago. All right, and the solar system came from a cloud of gas, mainly hydrogen, and lots of dust, and it was a very turbulent and dynamic place. And you can see here in this simulation that things are clumping together, and gradually, as the dust and gas clumps together, it forms a central star with a disk around it. And as the disk circulates, it clears, the dust clumps together, and the influence of gravity makes those clumps and clears spaces within the protoplanetary disk where planets can form. And there you see the simulation. And on the right-hand side, you've got something which is real. And these images that have come from the ALMA telescope, the Atacama Large Millimeter Array Telescope. These images blow my mind in a way that few things do. This is a picture of a real star, TW Hydra, in the center. And surrounding it is the disk of dust, and the spaces, I don't know if you can see my cursor or not, but the spaces in this dust is being cleared. These are where planets are forming and clearing the disk. And to me, over the last sort of 10 years, when we've started seeing these amazing images, this is utterly mind-blowing, that a lot of the theories that we've had are actually being shown to be true, which is hugely amazing. So we've always assumed that there was a cloud of gas and dust in part of a nebula, and it started to collapse under gravity, and it coiled around and around and around, and the dust cleared and planets formed. And we're saying, hey, yeah, actually this is what is happening. It's for real, which is great. Now I don't want to start that one again. So this is what has happened then, and this is what we've now got here in the solar system. We've got the sun in the center, obviously. We've got our 4 rocky planets and the moon, and Mars has 2 of its own little moonlets. We have the gas giants, Jupiter and Saturn, Neptune and Uranus, the giant ice giants, the asteroid belt separating the rock from the gas and the ice. And then right out here, we've got Pluto, which is no longer a planet, but it's a minor planet. And it's been promoted to being a Kuiper belt object, which is fantastic for Pluto. And there are several other of these objects that we know about now in this belt of objects which are made of rock and ice. So there's a huge amount of stuff in this solar system, in this planetary system. And the objects I'm going to be talking about have more or less all come from, or a lot of them, most of them have come from the asteroid belt. Now, the the Earth is about 150 million kilometers away from the sun, and the asteroid belt is almost double that distance away from us again. And so that's why these objects that come to us from the asteroid belt are voyages in space, because they've come across all those millions and millions of kilometers to get to us. But they're also, I call them voyages in time, because they are 4,567 million years old, and I'll explain shortly how I know that very, very precise number. And so they are holding within them information from the dawn of the solar system. Asteroids, when we look at them close up, cover a whole variety of compositions. What I've got here is I've got Ceres on the left and Vesta on the right. Ceres is the largest of the asteroids. Of course, I've got them, not on the same scale. This is about 1,000 kilometers across, and this is about 500. This is about half the diameter of Ceres. Ceres is asteroid number 1. It was the first asteroid that was observed, and these pictures both came from the NASA probe, the Dawn probe, which a few years ago toured extensively between Ceres and Vesta and took these amazing close-up images of them. Now, what you can see from Vesta is that it's spherical, all right? And this is why it's a minor planet as opposed to Vesta, which is just an asteroid. So it was big enough to self-gravitate, to form a sphere, and that's the same with Pluto, but it's not big enough to have cleared its orbit. So that's why it's a minor planet and not a major planet. And what it is actually is it's undifferentiated. So it's made of the stuff that the solar system was formed from. And it's more like a sort of compressed ball of mud rather than rock, and it's got a sort of tough crust of almost sort of solid clay type material, and then underneath it it's got a sort of slurry of more mobile muddy stuff. It's probably cold in as much as it doesn't have a central hot core, but it's very interesting that it's still got a certain amount of water within the surface and within the underlying layers. And this very bright material here within one of the craters is known to be some salts, so not quite sodium chloride like we have on our fish and chips, but salts of carbonates and sulfates, which have been produced by the evaporation of water. So Ceres is what we would call quite a primitive asteroid. It's almost certainly got a lot of carbon in it, a lot of organics, as well as clay minerals, which hold a lot of water. Almost at the other end of the spectrum, though, is Vesta. Now, Vesta is differentiated. So that means it's been heated from the inside, and the rock that it was made from has melted and changed into a different type of rock. So the rock that Vesta is made from is a basalt. It's the same sort of stuff that we get coming out of volcanoes and flowing through. If you think of pictures that you might have seen of the volcanoes in Hawaii that are continually erupting, you can see the sort of lava spilling down the side of a volcano and then quenching and solidifying. And this is the sort of thing that has happened to Vesta, and it's very hard, very solid, and it probably at one stage had a big metal core, but if you turn Vesta around, if you looked at it from the other side, it's got an enormous great hole in it. It's had a huge amount of material removed from it by collisions. And this is a message you can see from both of these, both Ceres and Vesta. They are covered, they're pitted with these craters. Now on Vesta, they're very clear, and on Ceres they're a bit more smeared, and that's because Ceres has got this sort of softer, more muddy, solid clay crust, whereas Vesta is rock, and you see that. And these are the extreme types of object that send meteorites towards us. So let's go on to the next one. So what types of meteorite do we get then? Well, traditionally, and this is where I teach you all to become classifiers of meteorites, traditionally we had iron meteorites like this one here. This is a slice through an iron meteorite, which are made of iron, and stony meteorites, which are made of stone, and stony irons, which were a mixture of stone and iron. So they were the three old classifications. We don't classify meteorites like that anymore because it doesn't tell you very much. It tells you, okay, yeah, sure, it's made of iron, sure, it's made of stone, but it doesn't tell you about the processes that these meteorites have gone through and what we can learn from them. So our modern classification now is we talk about things that are primitive and they're undifferentiated, and they're chondrites, and I'll explain all these words again in a minute, as opposed to the processed meteorites, which are partially to fully differentiated, and we call them achondrites, okay? So this one is primitive, and these two are processed. So what does that mean, and why is it important? Right, well, these are primitive meteorites, and this is actually an animated GIF of the foot of the OSIRIS-REx mission to asteroid Bennu, and this thing is called the TAG, and I can't remember what TAG comes can't remember what TAG stands for, but it doesn't matter. What it does is it comes down onto the surface of Bennu, and you can see that the surface of Bennu, this asteroid, it's a bit like Ceres. It's covered in boulders and it's relatively soft. And this is collecting material from this particular asteroid and bringing it back to the Earth, and it'll be back to Earth in a couple of years' time. Okay, so primitive asteroids then are things that have not been melted, and they're made up of these objects called chondrules. Now, a chondrule is it comes from a Greek word chondros, meaning droplet, and you can see these very round textures, and this is a sample of a meteorite called Allende, which fell in Chile in 1969, and this thing that's on the top of it, which looks a bit like a bird dropping, isn't a bird dropping. It's like these other bright things which aren't circular in shape, which are calcium aluminium inclusions. Now, what these objects are showing us, the chondrules and the calcium aluminium rich inclusions, why these meteorites are, go back again. Yeah, and why these meteorites, we call it primitive, are because they have the composition, and this is going to sound really bonkers, but they've got the same composition as the sun if you take all the hydrogen away, all right? And you might think, well, hang on a minute, the sun is 99.9% hydrogen and, 0.2% helium or something like that. So what else is left in the sun? Well, you've got iron and carbon and magnesium and silicon and phosphorus and uranium, and all those other elements are present in the sun. And they are present in the same relative proportions in these meteorites, these primitive meteorites. And this means their composition has not changed radically. They might have been heated a little bit, they might have been altered by water a little bit, but they haven't been heated so hard that the rock has melted. So these primitive meteorites are telling us about the material from which the planets were first made. And when you look a bit more closely about what those objects are, these are calcium, and this is a close-up down a microscope of one of those calcium and aluminium rich inclusions. All right, now I just want to check something here. I'm looking at my screen, and what I've got on the top of the screen, I've got the toolbar, which tells me, the microphone's on, my video's on, there's one message in the chat, and it's covering all the titles of all the slides. Can you see that or not? You can. Oh, right. Yeah, shall I try and move it? Can I move it? Can I move it without? Has that now moved down to the bottom? I hope that's moved down to the bottom so you can.
We can't see it at all, so it's fine.
Okay, jolly good. All right. Okay. So here's a picture of a calcium and aluminium rich inclusion. And right, what you can see about it, okay, the scale bar shows it's 2 millimeters across. It's a bit fuzzy. It's very irregular in shape. And the irregular shape tells you it's not been formed from something that's been molten. All right. So this is something which is probably a solid come directly from a gas. It hasn't gone through a liquid phase which allowed it to form a little sphere. It's called a calcium and aluminium rich inclusion because it's made of minerals that are very rich in calcium and aluminium. So we like to keep things very simple in the meteorite business, all right? So the minerals are rich in calcium and aluminium, and those minerals are the type of minerals that furnaces are made from, and the inside of your oven is made from, because they can take they don't melt until really, really high temperatures, about 1800 kelvins, sort of 1600 degrees C. So these objects were the first things that formed as that planetary disk, as the solar nebula was collapsing and the planetary disk was forming. These were the first objects that solidified out of that dust. The next set of things that formed were possibly, maybe, the chondrules. Oh no, now what have I done? Next, let's go to the next slide. Right, okay, so chondrules, these are these things that were little droplets, right? So again, my slide bar here is 2 millimeters. This is a section through a rock. This is what meteoriticists and geologists do when they examine a rock. They take a very, very thin, they saw a thin slice from it, polish it down so it's only about 30 microns thick, so you can shine light through it. And this has got light shining through it, and you can see these funny little round droplets. And this one is a close-up of one of those round droplets, and it's you're looking at it through crossed polars. Now, what that means is if you think of putting on a pair of sunglasses, you polarize the light. So when you're looking at the sea or something like that, you don't get the sort of bright reflection, the too much sparkling. Now, with this, we've put two pairs of sunglasses, one going like this and one going like that, all right? Two different angles. And what it does is the light, as it comes through the thin section, is rotated a little bit, and you get all these wonderful colours, really, really beautiful colours. And, you know, I was knocked out, you know, majorly knocked out by things like this when I first saw them, and the thin sections of the moon, almost as majorly knocked out as I was by the picture of the protoplanetary disks from ALMA. But then again, I'm very easily impressed. But these objects are different from the calcium aluminium rich inclusions. You can see straight away, you can see they're round, but actually, if you look at in a hand section, hand specimen, they are spherical. So, you know, they're spherical, and they're made of iron and magnesium silicates. So if remember, the CAIs were not round, and they were made of calcium and aluminium rich oxides and silicates. And the difference between the two objects, the CAIs and the chondrules, is temperature. So, no, it's two things, temperature and mode of formation. We think these were formed either by collisions between dust particles or by flash heating, because when the solar nebula was forming, there was a lot of friction and a lot of static electricity, and there would have been lots of bolts of lightning. So we don't know whether it was flash heating. Now, I keep saying these primitive meteorites weren't heated, but these components in them, the chondrules, you get two dust grains knocked together like that, and they melt and instantly quench. And in that instant, you get this little round ball. And the first person who looked at them in a meteorite, in a thin section, was, about 200 years or so ago now. And he called them droplets of a fiery rain. And that's a really beautiful and compelling image. If you think of raindrops as being drops of water, these are drops of silicates. And they're high temperature, 1500 K, 1200 K, so maybe 1200 degrees C. So they formed at a lower temperature than the CAIs. So you've got a difference in formation temperature and a difference in formation process. Do we have a difference in formation location? Were they formed in different parts of the solar nebula? Well, that's a really big question that we don't know the answer to. So that's a matter of active research at the moment. Now, the timeline for the formation of these is really interesting. So here I've got 4567.2 plus or minus 0.6 million years, all right? That's this red dot here. And so I like to call that the year dot. All right, this is when the CAIs formed, 4567.2 plus or minus 0.6 million years ago. Now, if there's any astronomers around, they'll say, oh, the sun formed about 5 billion years ago. And if you'll then go to them, you can say, no, it didn't. It formed 4,567.2 plus or minus 0.6 million years ago. You know, don't be, you know, this is very precise. And fortunately, it's also very, very accurate. And the chondrules, they formed a very tiny gap, 4564.7 plus or minus 0.6 million years ago. So you've got 3 million years in time between the formation of the CAIs and the chondrules. Now, we can be sure of that time difference because the way that we measure these is we take some of those components, all right, like these chondrules or like the CAIs, the minerals, and dissolve them up and extract the lead from them. And we can measure the lead that's in them. And lead has several isotopes, some of which has come from the decay of uranium-238, and some of which has come from the decay of uranium-235. And by taking the ratios of the different lead isotopes that has come from those different uranium isotopes, we can then determine the date. So we can age date these, because uranium-235 and 238 have different decay rates and different decay products. So by taking their ratio, we don't need to know how much uranium there was there initially, and we can measure how much lead there is now. Okay, so we can measure tiny quantities of lead and uranium, and get these very precise differences. And then the Earth was formed here, and then the Moon was formed about there, and all these sorts of things. So here I've got the Earth as just a solid ball, but by the time the Moon was formed, only a few tens of millions of years later, it has done this differentiation, which I will again come back to. Now, the really interesting thing about this is that this time scale, this difference of 3 million years, is a long time in terms of keeping dust and gas and keeping components apart. So if these objects, the Chondrules and the CAIs, formed in different reservoirs, we're not sure how they managed to stay apart, to get these, how the dust stayed apart, to get these different lead isotope ratios. So it's a mystery, and it's a matter of active research, which is really great, actually. Right, so where are we now? So, and the other exciting thing that's in these meteorites, which you can't see at all, all right, unless you're looking at a very using a very special microscope. So here, this is 200 nanometers, this scale here, and I'm talking about presolar grains. So these are the grains that have been produced before the sun, all right, presolar, before the sun. Now, I've gone into a great deal of time saying that, oh, we've got gas and dust, it's rotating, and it forms the sun. Now, the sun also throws material off. It has a solar wind, which is mainly of hydrogen atoms and ions, because that's what the sun's mainly made from, hydrogen. Now, some of the other stars that we know of in the galaxy are they're not burning hydrogen in the way that our sun does. They've burnt all their hydrogen. It's all been converted to helium, and they're now burning helium. And so their stellar wind would be made of helium. And some stars are even older, and they've gone through the stellar cycle and have got to a stage where they've burnt all their helium, and they're now burning carbon. And in their stellar wind, there are particles of carbon. So the grains reflect the type of star, the composition of the grains reflects the type of star that they've come from. So we've got diamonds, emeralds, and rubies. Okay, well, diamonds, carbon. Emeralds and rubies, actually, they're the same thing. They're both aluminium oxide, and silicon carbide is carborundum. And graphite is what you get in pencils. So all these things, you know, they've got very fancy names and sound really good, but basically they're all different minerals, different compounds that are being produced in the outflowing winds from different stars. How do we know? Well, the way we know this is because all these grains have gases trapped in them. All right, they've got xenon, they've got neon, they've got argon, they've got helium trapped in them as well. Now, we know what the neon composition of our atmosphere is. Neon's got 3 isotopes, xenon's got an unhealthy number of isotopes, about 9, I think, you know, far too many for its own good. Argon's got 3 isotopes, helium's got 2. Krypton, can't remember, too many again. But we know what the neon isotopic composition of the sun is and of our atmosphere, and we know what the nitrogen isotopic composition of the main parts of meteorites, so the chondrules and the stuff between the chondrules. We know what those isotopic compositions are. The isotopic compositions of these objects, this is diamond, and this is a silicon carbide grain. And what we're seeing is that they have really, really, really unusual gases in them. And when you measure the carbon isotopic composition of the diamonds and the silicon carbide, that's really odd, really, really odd. And the nitrogen's really odd. So for instance, if you, the carbon 12-13 ratio, do I want to do 12-13 or do I want to do 13-12? In our system, all right, there are 90 carbon 12 atoms for every carbon 13 atom. So the ratio is 90-1. Now, if you are in a star that's burning carbon, it's gone through all sorts of different phases, different processes, and actually the carbon 12-13 ratio, instead of being 90-1, it's 4-1. All right, so it's got a very, very different ratio of atoms of carbon in the isotopes of carbon. It's the same with nitrogen. And because we've got astrophysicists who can calculate what these ratios could be in terms of the physics of what's going on in stars, we can compare those with the things that we can actually measure. And remember, actually measure. And we can say to the astrophysicists, really sorry, mate, your theory's wrong. We can tell you your theory is wrong because we can measure this in the lab. And so over the last 20 years or so, and I've been really privileged because I was one of the first people to actually measure the isotopic composition of some of these solar grains, which was just fantastic as a young scientist getting going. To be able to work, because we do work together, the observational astronomers, the theoretical astrophysicists, the lab scientists work together to say, hey, you know, we found this, you need to change your theory, right, now you're predicting what we should go and look for, let's see if we can find it. And it's been a sort of bootstrapping, getting up, and so we can understand now a lot more about these presolar grains, where they come from. They've swept into the solar system. They swept into that cloud of gas and dust from different stars. Now, remember, you know, we're part of a galaxy. We've got nearest neighbours in terms of the stars that we know, you know, Proxima Centauri, 4 light years away. But there are at least 35, maybe closer to 50 these days, individual populations of presolar grains in these primitive meteorites, showing the neighbourhood that the sun was born in, so the stellar cluster it was in, and its companions, which is really, really amazing when you think, well, you know, here I've got something in my hand, it looks like a chunk of rock, but it's full of diamonds from beyond the beginning of the solar system. There's another set of stuff that comes from, that is interesting in these primitive meteorites. And this is a picture of the Murchison meteorite, which fell in Australia in 1969. And it is stuffed full of organic compounds. All right, it's stuffed full of aliphatic and aromatic compounds, straight and branched chains. It's got amino acids in it, carboxylic acids, all sorts of stuff. And the reason, again, that we can say that these are formed actually not in the dust cloud that the solar system came from is, again, because of isotopes. They are enriched in deuterium, so that's the heavy isotope of hydrogen, again in carbon-13 and nitrogen-15. And they have been formed in another molecular cloud, or a different part of the molecular cloud from which our system formed. And you can see that it's the different molecular processes that have actually built up these networks of organic matter. Now, they're mixed with organic matter that has undoubtedly come from the solar system. But again, we don't know what the mix is. And it's a really active area of debate, because when we study things like comets and some of these primitive meteorites, these are the building blocks of life. And there is no doubt at all that these building blocks were delivered to the Earth. And I'll carry on with that again in a minute. Right, so primitive meteorites are not melted. Processed meteorites have been melted. And this is where I want you to now think of steel making, right? Something which I think has been very important in Wales in the past, if not now, so very, very sadly. But in making steel, you take iron ore and you add coal to it and you melt it. And the reason you add coal is a reducing agent, and iron ore is iron oxide. And what happens when you heat them together is the coal, the reducing agent, pulls the oxygen away from the iron oxide, reduces it to iron metal, and the carbon dioxide it produces then just floats away. So you take your iron oxide and a reducing agent, and you reduce the oxide to a metal. And because most of the iron ores that we use for making steel aren't pure iron oxide, they've got other stuff in them. What happens in a furnace is you get all the metal comes to the bottom, falls down to the bottom of the furnace where it's tapped off to make steel. And at the top, you've got a slag. You've got all the slaggy stuff that isn't required and that's just left over. And that just because it's lighter, because it hasn't got any of the metal in it anymore, it's lighter, and that just floats up to the surface of the molten metal. And that's exactly what has happened with processed meteorites. So they have been hot enough inside to melt. Now, they're not made of iron oxide, they're made of iron, magnesium, calcium silicates. And there's plenty of reducing agent in there. There's sulfur and there's carbon. And so right at the start of the solar system, these things were melting and differentiating. The different layers were being formed. The core, and this is what's happened on the Earth, we have a metal core and we've got a layer above it where you've got a mixture which is part metal, part silicate, and right on the top, the bit of the Earth that we walk on is the equivalent to the slag in the blast furnace. And these meteorites here, this one, the stony processed meteorites, they are the equivalent to the slag from an asteroid. And so what you can see here is you don't see those chondrules anymore. You see broken fragments of materials. And this would be what you would see if you looked at a thin section of a basalt on the Earth. You'd see these same minerals. It's a mineral called plagioclase and a mineral called pyroxene. These are mixture. These are the very earliest of solar system basalts. And this is what Vesta's made from, okay? Now, the final stage is the core of the Earth, which is metal, okay? And it's the same with the core of asteroids. They're made of metal. Not just iron metal, but iron nickel metal. And you can see that here. This is a slice of a huge meteorite, huge great big iron meteorite. It's been sawn, it's been polished, and then it's been very, very lightly etched with acid to bring out this a strange, very strange pattern. And it's called the Widmanstätten pattern, and it's absolutely characteristic of iron meteorites. Now, what happens is in your furnace, in your asteroid, the iron, it's not pure iron, the solar system iron, is a mixture of iron and nickel. And what happens is, as the metal cools, the iron and the nickel, they're completely mixed up together. But as the metal cools, and they cool really slowly, the iron and the nickel atoms, they want to form their own lattices. All the iron atoms want to be with other iron atoms, and the nickel atoms want to be with other nickel atoms. And so they start to segregate, to separate out. But by the time you've got to about 700 or 800 degrees C, the atoms don't have enough energy to move anymore. So you've got this sort of mixture of bits where you've got a bit more iron and a bit more nickel, and you've got this amazing pattern. Now, these things are cooling at a rate of 1 degree every million years or something like that, which is quite a long time. If you think of tapping off metal in a furnace, it cools over, what, 24 hours max? And so what happens is any impurities in the iron that have stayed in the iron, and things are added like manganese and stuff to make different types of stainless steel, different types of steel. And so they don't have time to move. So a terrestrial steel does not have this pattern. So this is one of the ways that we can tell an iron meteorite. And so these are from the core of asteroids. We can't get to the core of the Earth, it's too deep down, but we can get to the core of an asteroid because it comes to us as an iron meteorite. Okay, so what time is it? 1913. Oops, I better accelerate. So we have some meteorites from the moon. As you know, the moon is completely covered in craters. I've been talking about meteorites from asteroids up to now, but we've got meteorites that come from the Earth. You can imagine an asteroid coming in, hitting the moon, bouncing material off, and it falling to the next nearest place, which is the Earth. And we can prove that these meteorites, and this is a picture of one of them, this is the first one that was recognized as lunar. We know it's made from the same stuff as the moon. It's got the same age as the moon and much younger than meteorites. Remember that picture I showed you, the formation of the moon was much later than the formation of asteroids. It's got the same composition of minerals and the same composition of gases in the moon, in these, trapped in the moon. And we know this because we can compare these with the rocks that the astronauts brought back from the moon. And they did go to the moon and they did bring rocks back. And very shortly, we'll be sending some more to the moon. And we've had more rocks come back from the moon. The Chinese mission Chang'e 5 has brought rocks back from the moon. And we've actually hoping to get some at the Open University to analyse fairly soon. Eventually. So we've got rocks from the moon. Now, they're from different parts of the moon. The moon was only about 5% of the lunar surface was explored by astronauts. And so these come from different parts of the moon, which we can tell from although I say they've got the same composition as the moon, the same oxygen isotope composition as the moon. We think they've come from different parts. So we can explore more of the moon using these meteorites. Now then, meteorites from Mars. We've definitely got meteorites from Mars as well. You know, you can think again of Mars. It's been hit by asteroids. They've thrown rocks off. Yes, they've got further to come than rocks from the Earth, but they're gradually pulled in to the center of the solar system, to the sun. And most of the asteroids, well, most of the asteroids that come from the asteroid belt, that come from Mars and from the moon, get just pulled straight into the sun. But some of them have fallen to the Earth. Now, we haven't yet had any meteorites recovered. We haven't yet had any rocks brought directly back from Mars. We know a lot about the composition of Mars from the rovers and the missions that have been there, but we haven't had anything brought back directly. So how do we know these are from Mars? Well, first of all, we can see that they have got these. This is a piece that's about 8 kilograms, I think, this rock, and it's been cut in half. And these lines going across, they're not significant. They're from the saw. What you can see, though, in here, though, are these black patches. Now, these patches are of glass. Glass in meteorites is usually formed by shock. Something hits, again, like those little chondrules, they melt and then they quench. Now, these bits, you can fertile them out. And when you get them out and melt them, you can actually measure the composition of the gases in these rocks. Now, this is a composition. This is a very old slide, actually, from 1980 something, 5 maybe, when these were first recognized. And at that time, we hadn't had anything beyond Viking, all right? So the new era of Martian exploration hadn't happened. And what you've got here is a composition of Mars's atmosphere plotted against the composition of the gases that have been removed from these impact glasses. And you can see here that this is a straight line. It's a log plot, but it's still a straight line. You've got a really good correlation, and not just between the actual elements, between the isotope ratios. This is showing a 40 to 36 ratio of about 3,600. Now, the terrestrial atmosphere has a 40 to 36 argon ratio of 300, so it's definitely not. And here you've got your nitrogen. Now, these measurements, xenon, krypton, neon, argon, and nitrogen, they were measured at laboratories in Minnesota and in Houston. This was measured at a laboratory in Milton Keynes. And this is my measurement. Again, I was one of the first people. I'm sorry, I'm blowing my own trumpet here. Don't know why I'm doing that. But this is one of the first measurements showing that the carbon dioxide, which is the main constituent of Mars's atmosphere, is present in these rocks. And the only way you can get such a marvelous match between the gas in the glass and the gas in the atmosphere is if the rock has come from Mars. All right. So, the analogy a lot of us use is that, just as Blackpool rock says Blackpool all the way through it, these rocks say Mars all the way through it. Now, most British people know what seaside rock is. You try explain that to a Japanese colleague and they don't really get it at all. But these rocks have come from Mars. Now, if they've come from Mars, then we can start learning about them from Mars. And one particular meteorite, Allen Hills 84001, has been altered by water. Like many of the Martian meteorites, has been altered by water. It has carbonates in it, which has been produced by water, and warm water at that. And these particular rosettes of iron, magnesium, calcium carbonate contain magnetite. That's these little black bits here. And some colleagues in 1996, so a long time ago again now, broke open one of these rosettes, looked at it in an electron microscope and thought they'd seen a little petrified bug like you can get at some limestone springs and things like that. And they announced they'd found life on Mars. Well, nobody really believes them, but what this did do was it kick-started, it gave a huge impetus to the exploration of Mars. And, this has been going on. We've got Perseverance now with its little helicopter Ingenuity. We've got Curiosity. We've had Phoenix, all sorts of things. So we've got Mars 2020, which is collecting rocks. The Perseverance rover is collecting rocks. It's about here at the moment. I believe it was over here, or maybe it's about here. I can't remember. Anyway, so it's collecting rocks. It's part of the Mars Sample Return Initiative. ExoMars 2022, unfortunately, has been put on almost permanent hold. It was going to be launched in September from on a Russian rocket from Baikonur, but of course the European Space Agency has now withdrawn all contact with Russia, and so that mission has gone on to the back boiler. But we still have the Fetch and Return rover, which is going to launch in 2026, hoping that the samples arrive back in 2032, just in time for my 75th birthday. Okay, so I'll be looking forward to analysing those samples there. And the reason that people want to look at this is because they think that maybe there's some form, possibly some form of life on Mars. Could there have been life on Mars? Well, the thing is that when the Earth and Mars were forming at the same time, the Earth, being closer to the sun, was much, much hotter. Its surface was completely molten. It had an atmosphere of steam. Mars, further away, made from the same stuff, smaller, cooler, cooled more quickly. Atmosphere became, it still had an atmosphere which had plenty of water in it. All the ingredients for life were present on Mars earlier than, and the conditions for life to get going were present on Mars earlier than they were on the Earth. So it's just like, right, that's a real driver. So what can you learn from meteorites? All right. Well, you can learn about the origin and evolution of the solar system. Now, I've talked about the CAIs and the Chondrules. You can learn about the origin and evolution of planetary systems. All right. So, and that brings in exoplanets. So we've talked about the way stars form and the way planets form, and we can work really well with the astronomers who are using ALMA and other telescopes to do that. We can talk about stellar evolution, and that was from the presolar grains and from the interstellar grains, the organics. We can talk about the formation and the evolution of the moon and the formation and evolution of Mars, and explore Mars in different ways, explore the moon in different ways using these particular meteorites. And we might even be able to say something about the origin of life. So that's not bad. All right, so I'm on, no, I can't be on slide number 2 of 20, but I've talked for about 40 minutes. Just let me look, just move my presentation down a bit on my other screen. Where have I got to? All right, I'm on slide 18 out of 30, which is pretty bad. And so I'm not going to say anything. I shall just, I shall just say, where can you find meteorites? You can find them in the Antarctic, or they fall on the drive. This is our latest one, which fell in Winchcombe. We can go to a comet, and I'm not going to go anything more about a comet. Let's go straight through all that. But one of the things that I want to say is that why do we do exploration? All right. Why do we go to things like comets? This on the left, that's Sasha, and this is Sasha, and this is the instrument that I use to measure bits from meteorites. All right. And you can see Sasha is 6 foot tall and he's standing there, and it's a pretty horrendous bit of equipment. On the right, we've got Andy Morse with the Ptolemy instrument, which is the same as the thing on the left, except shrunk to the size of a shoebox, so we can send it to Rosetta, which it did. And what it did there, Rosetta, is it sniffed the organics, sniffed the gas. All right. And once you've got something that can sniff a gas, you can use it for all sorts of things. So one of our cases in the REF case was using the technology, the space technology, to test the atmosphere in submarines. So if the CO2 concentration rises too much because the air isn't circulating well enough, the alarm goes off in time. And we can do all sorts of things. And Taff, who does this, is very happy with his whiskey tasting. He's looking at adulterated whiskey to see if you can test the difference between it and the real stuff. And he says you can, but he seems to have to keep doing more and more tests. I'm not entirely sure why. But anyway, sorry, major gallop through the second part of my seminar. You just have to ask me back again to talk about a bit more about meteorites. Anyway, thank you very much, and I'm happy to take questions.
Monica, thank you so much. That was wonderful talk, really illuminating and interesting gallop through the solar system and its origin. So thank you so much for that. If anybody has any questions for Monica, they can drop them into the chat and we'll pick them up from there. And perhaps while people do that, I'll ask a quick question, if I may. And that is, can you use lead isotopes to date the pre-solar grains? And if so, what age are they? And does that tell you anything about their origin?
Yeah, the problem with the pre-solar grains, most of them are too small, really. Okay. And you can date little clusters of them. And yes, you can use lead isotopes for that. And some of them, well, the first sets of measurements showed that they were older than the universe, which was a bit disconcerting. I think they're showing to be between 5 and 7 billion years old. So definitely older than the solar system. Okay,
great. Any questions from anybody in the audience? And if not, I should say your ref case study sounded very interesting as well. In terms of submarine.
Yeah, I'm sorry.
Fingers crossed for it.
Yeah, I'm sorry I went through that so fast, but the thing was that our submarines were using American technology, which was about the size of a very large 4-drawer filing cabinet. And a rating used to have to come down 3 times a day to take a physical reading and take a bit of paper back up to the captain on the bridge or the admiral or whatever from one place in the submarine. Now, with Analox and British Aerospace, these are being fitted in all our nuclear submarine fleet, or one of it, or 2 of it. And there are several of these sensors all around the submarine, and they can be read directly from the bridge. And so it's much, much safer. And it's also saved us, I don't know, about £30 million.
Okay. So there's a question from Shu on Ceres. Why is it not differentiated, given it was big, or so big? Did it form in a region with less radioactive isotopes?
Well, that is a mystery. And if you could answer that for me, I'd be really, really happy. This is one of the things that we still don't quite understand, why some objects did differentiate and why some didn't. It's more likely they formed later. So for a long time, people thought, the primitive stuff must have formed first. And then some of them got hot and differentiated, and the ones that didn't get hot didn't differentiate. And that makes no sense whatsoever. So if you've got radioactive isotopes and something gets hot, and then you've got the isotopes decaying, and it wouldn't have been from the uranium so much, but aluminium-26 is one of the really short-lived radionuclides, which would have been live at the start of the solar system, provided the heat for the melting, and then as it decayed away, maybe that's when Ceres formed. So it wouldn't have been after the uranium had decayed, but the aluminium-26 and a lot of other very short-lived radionuclides. And I should say at this stage, no meteorites are radioactive. They're not radioactive anymore. So so we can only think it's because they were maybe formed slightly further out. So they weren't getting the heating from the sun, and they also were forming slightly later on.
Okay, so I'm going to jump to another question from Kelsey. So she says, you loved the lecture. It was very insightful. Just asking, how you first became interested in this field of research.
Well, I think it definitely comes from my childhood. In that I'm from Leeds, the what do we call Yorkshire? The king of all the counties. Leeds is in a bit of a sad situation at the moment, probably going to go down into the second division or whatever they call it these days. But I grew up in Leeds, had a very, very happy childhood, and loved going out into the Yorkshire Dales. And trying to understand what I was seeing, because there are some amazing places, a place called Brimham Rocks, for one thing, where you've got amazing structures in the limestone and the sandstone. And that caught my imagination. And so that's why I went to do geology at Durham, and chemistry as well, because I really, really loved chemistry, still do. And then when I was in my final year at Durham, we were really lucky. And if you're, sorry, I don't know, because I can't see you, I can't tell whether you're, a school student or a senior citizen or what stage of anything you are. But if you're still at school or at university, you're able to do this as well, is borrow material from our research council. And we borrowed a package of these thin sections which came from the moon. And when I saw, like I say, I'm very easily impressed, but when I saw the thin sections that come from the lunar rocks, again, mind blown, because they were so clear. So when you look at some of the rocks like that one from Vesta, they're cracked and they're shattered because of the way they've been, the way it's been formed. But even worse are rocks on the Earth, because they've been rained on, they've been snowed on, they've frozen, they've got plant roots growing in them and all sorts of things. And so they tend to be not quite so clear. The lunar rocks were like stained glass windows. They were absolutely beautiful, pink and blue and yellow and green. And I wanted to understand why that was, why they were different from terrestrial rocks. And I was really lucky, because then I also wanted to go to Cambridge, because that's where my boyfriend at the time was going. And I was really lucky to find a PhD going in Cambridge, which was to study lunar rocks and meteorites. And it's just like, and I've kept going from there. I kicked my boyfriend into touch and married somebody else. So.
Great. So another question. So sorry, this might be a bit out of the scope of the presentation, but it's a curious question. And that is to ask if the mechanical properties of glass found in the meteorites has ever been evaluated. So they're aware that there's been a bit of testing done on rocky and iron meteorites, but never seen anything on the glass. So that's the mechanical properties of the glass.
Yeah, I mean, I guess we do know the mechanical properties of the glass. They're very similar to, a lot of them are similar to obsidian, which is the volcanic glass. So they're produced, again, by shock. So you've got that very, very high pressure, but for a very short period of time. So it's not like where you've got the obsidian, which is, being produced maybe at depth and being thrown out from depth, but you've got the high pressure. So the properties are slightly different, but you've got things like conchoidal fractures and all sorts of stuff. But I don't know what the pressure loadings are and things like that. Okay. But there have been some studies done of them.
Great, thank you. And then a question here from Barbara. What was the value of your studies in prostate and colon cancer?
Well, what that was for diagnosis purposes. So one of the things that we can do is, if you get, if you're breathalyzed, you blow into a tube and, some crystals turn colour. It's not quite got to that stage yet, but if you take a breath test, your breath reflects the composition of what's going on in your body. So that might be particular compounds that are produced by cells at different parts of their lifetime, or by bacteria that you've got in your body. So by looking at the products of the cancers, you can tell. With TB, the testing was looking at the it was saying that actually we don't have to what's the word? We don't have to culture the sputum to actually get enough to see that it's got TB in it. Again, you could do it from a breath test. So it's a much swifter diagnosis. And it's one of those things that, right, well, okay, if you can get to a stage where you blow into a bag and they can say, 80% of chance that you've got prostate cancer, now let's go and do the more invasive test. It's quicker testing.
Right. Thank you so much for your presentation this evening, and thank you very much for answering all of those great questions. They were really excellent. There is one final comment here from Edward, which is kind of doing my job for me, and that is about thanking Diane Edwards for convening this whole series of talks on Voyages of Great Discovery, and of course that's culminated with Monica's fantastic talk tonight. So I will say thank you, Diane. I'll hand over to you just to say final thanks to Monica and everybody.
Well, before I I will thank Monica. That was great. I feel that my grandson is 7 years old on Sunday. I've learned an awful lot of the planets from him, including the fact there's not many planets in Jodrell background, are there? So I will now come armed with the meteorite business.
Well, my grandson was 7 last Sunday, and he's obsessed with the Titanic.
Oh, well, that's maybe a bit easier. But thank you so much. It's really great of you to come when you go. You obviously are passionate in other ways. And next time, I shall have to think of another topic, or if I ever do another series, I'll think of another topic which might entice you back here. So thank you.
It's been my pleasure.
There will be a series in the autumn. I dread to think where it might be or who might be there, but I'm already looking for people who might be able to talk about sustainability and various forms of sustainability and how we're going to combat the various challenges of creating a sustainable existence on this earth. So I think that's going to be the one which will be on the second Tuesday of September. And hopefully it will be here in Cardiff, and hopefully it will be in our lecture theatre, so we can meet you all again. So thank you all for joining us in such difficult times, and particularly now. And I thank to us people like John Evans and people in the university who actually got us to this webinar or Zoom series. So it's thanks all around. And, I look forward to seeing you all in the autumn. Thank you again, Monica.
Okay, it's my pleasure. Thank you very much. Bye-bye.
Not quite yet. Jumped off, has she? Oh yeah, no, she has. Right, okay.
Oh, well.
Right, shut down.